Let's explain containers both from top down and from bottom up. Here are the terms that we are going to use in this episode: cgroups, namespaces, UFS, hypervisor, user space, and kernel space, and more. And of course, we are going to describe what each means and how it relates to containers. VMs, virtual machines, you are probably already aware of. So in VMs, we have a kernel for each virtual machine. So let's say that you have two virtual machines on the same computer. Each virtual machine, we have the Linux kernel, and it would speak to the hardware, but not directly. It would speak to the hardware to a common kernel. So you can imagine a few boxes of VMs. Each such box, each such top box has its own kernel, and all these boxes sit on top of a hypervisor, which is its own kernel. So you have an underlying kernel, this is the lower box, and on top of this lower box, which is the hypervisor kernel, you have multiple VMs, each with its own kernel. So if you have two virtual machines, in total, you have actually three kernels. A kernel for each virtual machine and a kernel for the hypervisor. On the contrary, if you have a container, then you have only a single kernel. You have only, let's say, the Linux kernel, which sit on top of the hardware, and then all the containers are just processes. Okay, those are just processes which use the same kernel. So here you already see the efficiency benefits because you have only a single kernel. You don't have the virtual machine kernels speaking to the hypervisor kernel. You have only a single kernel. All containers are just processes. The processes are limited by three terms. One is cgroups, one is namespace, and one is UFS. So we said that we have kernels, we have cgroups, namespaces. Let's define what each of these means. We'll start with the kernel because before we actually going to explain containers, let's define what is a kernel. Because there is no such thing in reality as a kernel. It's only something that we name, we give it a name. We take a piece of software and we give it a name. Different people also might name things differently. So when we say a kernel, we mean this. We have the hardware. The hardware is the most lower level that we reference in our case as software developers. This is not a kernel. Okay, so the hardware is not the actual kernel. And now we have the hardware and we have a few layers of software on top of it. So imagine two boxes on top of the hardware. You have the hardware on the lower level, and now we have two boxes on top of it. The next box, which sits right above the hardware on our use case, is the kernel. And the layer that sits on top of the kernel is the user space. The user mode is all the applications on the second box on top of the kernel box that you actually run. The kernel is the lower level. It is the virtual memory management. The kernel is the scheduling. The kernel is the connection to the hardware devices. It's managing all of this. It's managing the virtual memory, the management of scheduling, the connection to the hardware devices, and the network drivers. It's basically an abstraction on top of the hardware plus all the basic operation system services such as threading. So we have one box which is closer to the hardware. It contains of itself a few layers, and the second box sits on top of the kernel box, and this is the user space, which contains library to communicate with the lower box. You communicate from the user space into the kernel space with system calls. The lower box is the kernel. It contains all the hardware abstraction layer, all the thread scheduling, all the interrupts, and all the other lower level services such as memory management, power management, etc. The kernel is like the bare bones of the hardware plus all the operation system on top of it which manages the hardware. The layer which connects the user space, which is the box which sits on top of the kernel box, is using system calls in order to call from the user space into the kernel space. We have not described yet what cgroups, namespaces, and tarballs are. The containers are actually built from these components. The containers are built from, if you want to build by yourself a container, then you would need to deal with the cgroups, the namespaces, tarballs, and containers are just processes. Let's elaborate on this process. So the premise is this: you can package your application in a container and then just run it in your dev environment, in your integration environment, and also in production, because all would be bundled inside a container. This is its purpose. It's called a container because it contains something. What does it contain? It contains your application, but not only does a container contains your applications, it also contains limitations on your applications, and you achieve this limitation and separation from other components, from other processes, just as with virtual machines, you would achieve this separation with the separation of the whole kernel. Now we are not separating the whole kernel, we are just separating the cgroups, we are controlling the processes, we are separating processes on a lower level. If you take a machine that runs multiple containers and you run the ps command in order to see all the processes that are running on this machine, you would not see a process named container. Okay? What you would see is multiple processes, simple processes like Java processes, Python processes, Ruby processes. And except for the Docker daemon process or the other container management process, all your actual processes would look like simple processes. They would have a PID, you would be able to see them with PS, and you would not see something that mentions that they are containers. So what does make these processes containerized? They appear to be super standard and boring processes with standard process output from the ps command. So containers run as standard processes, and this is opposed to the case where you have multiple virtual machines, which is like a full-blown kernel that you run, and on top of it you run your processes. When you create a container, you take your code and you zip it in a tarball. Then when you run the container, the tarball is actually being unzipped and you run it as any other process. However, just like virtual machines, you do want your process, your container to have some limited access to disk and to a CPU. This is why you use the cgroups, which would limit the memory and CPU and other resources which are provided to your container. So each container is tying up together cgroups, namespaces, and UFS, Unified File System. This is a container. It looks like just any other process. The target of the namespace is to isolate and limit what you can use. For example, you would have a separate process ID, and all the processes from a certain namespace PID would not be able to see the process IDs and the other processes from other namespaces. So processes from one namespace PID, for example, let's say that we have my app1 namespace PID, they cannot see the processes from my app2 PID namespace. So the namespaces isolate and limits what your process in the container can see. Okay, and the cgroups limits the resources that are accessible by your container. For example, they limit the access to the CPU or the memory. So the basic definition is that you use cgroups, the containers. Docker does this for you behind the scene. The cgroups limit the access to the resources such as memory and CPU and others, and namespaces limit what your container can see. So one is limiting what your container can see. It cannot see other processes which are in other namespaces, and the cgroups limits what your process can do, how it has resources and access to the CPU and the memory. With virtual machines, we actually have multiple kernels, and with containers, we have a single kernel. So as we said, if you have two virtual machines, we actually have three kernels, two kernels that are a kernel for each virtual machine and one kernel which provides as the hypervisor. So one important thing to know about containers, now that we described that containers are just an abstraction above the cgroups and the namespaces, is that the correct usage for containers is usually when you have stateless applications, because containers are just processes, and processes can go up and down, and they have limited access. You limit the access into the disk and into other processes. So there is a whole lot of effort which is involved by managing containers, because once these containers are getting limited by the resources, then you need to know how now to handle security and how to handle the networking and how would these containers access other applications. And all this involves time and effort, and you need to write tooling around it. So to wrap up, when you have multiple virtual machines, each virtual machine has its own kernel, and all these kernels communicate with the hypervisor kernel. So on total, if you have three virtual machines, then you have four kernels. One kernel is the basis kernel, and three more kernels which are provided by the three virtual machines. But when you have containers, you have only usually a single kernel, because the single kernel is the single operation system which is running on the system, and all the other kernels simply do not exist because the containers are simple processes which are limited by the cgroups, which limited what the process can do and how many resources it's getting, and the namespace, which limits what the container can see or what the process can see outside. For example, my app namespace, if the container is in my app namespace, then it cannot see all the processes that belong to my app2 namespace, which is a simple process ID. So I hope with that we clarified some things with the relationship between virtual machines and containers.